Yellowstone is one of the most visited places on the planet thanks to the amazing national park with its dizzying number of attractions. However, visitors to the national park might want to be careful as a 100-foot wide crack has just opened up in less than 24 hours. What is causing the crack and what does it mean for the national park and its surroundings? Yellowstone National Park has something for everybody, which is why it's a popular destination for tourists worldwide. Among them is the Grand Canyon. The Yellowstone River carved this magnificent canyon, which is 20 miles long and 1,200 feet deep. Lower Falls, where the river tumbles 308 feet, twice the height of Niagara Falls, before striking the canyon floor with such force that it sends foam and mist hundreds of feet upward, dampening the rock so constantly that bright green moss grows high above the water, is its most famous and widely photographed feature. As the water races along and eventually stops foaming, it appears green, but it's completely clear. The river's color is caused by algae and moss. There is also the Mammoth Hot Spring, created by heat, water, minerals, and limestone all working together to form the famous feature, where variously colored travertine, a type of calcium carbonate, has been dissolved from the limestone beneath the ground and carried to the surface by rising springs of hot water. And despite the fact that some springs and terraces die, the total flow of water inside Yellowstone is surprisingly constant as new flows spring to the surface. Minerva Terrace, with its uncanny resemblance to an ornately carved staircase, is one of the most striking features here. There is also the mud volcano area of Yellowstone, which you'll smell before you see it. The noxious odor is caused by sulfur, which is also responsible for the mud's hissing and gurgling. The sulfuric acid in the pots eats away at the surrounding landscape, creating an eerie yet captivating, otherworldly atmosphere. Another popular area in the national park is the Upper Geyser Basin, which contains the most geothermal features in the park, including the famous Old Faithful Geyser. This is the place to be if you want to see a geyser erupt. The park can predict the eruptions of 5 large geysers in the Upper Geyser Basin. And all of these features have something in common, something hot and fiery that you don't want to encounter: a volcano. Yellowstone is known for being a place tightly connected with volcanoes, and the effects of the volcano are manifested in multiple ways around the park. However, a new manifestation is forming, and it is scary. In just 24 hours, the park developed a vast 100-foot wide crack. This forced the park authorities to close off a large section as they carried out urgent investigations to determine what was going on and what it meant for the area's topography. The fissure was discovered in an area known as Teton in the Wyoming section of Yellowstone Park. Meanwhile, Teton is no stranger to volcanoes. In fact, the rugged grandeur of the Tetons is the result of 4 geologic factors: tough, hard rocks in the core, vertical uplift, the age of the mountain-making movement, and dynamic forces of destruction. Many other mountains in Wyoming have equally hard rocks in their cores and an equal amount of vertical uplift, but they rose 50 to 60 million years ago and have since been eroded. The Tetons, on the other hand, are Wyoming's youngest range, dating back less than 10 million years, and thus have not been as deeply eroded. Any steep slope or cliff is especially vulnerable to nature's destructive methods. The Tetons represent a never-ending struggle between 2 opposing forces. The first is the rock's extreme toughness and, as a result, their resistance to erosion. The second factor is the presence of efficient transportation agencies that move all rock debris away from the mountains and away from the lower slopes. The majority of the Teton Range's rocks are among the hardest, toughest, and least porous known. As a result, they are resistant to mechanical disintegration caused by temperature changes, ice, and water. They are primarily composed of minerals that undergo very little chemical decay in the cold climate of the Tetons, and the absence of weak layers prevents the tough rock masses from collapsing under their own weight. All of these conditions favor the preservation of steep walls and high rock pinnacles. Nonetheless, they do degrade. Great piles of broken rock or talus that festoon the slopes of all the higher peaks bear witness to erosion's unrelenting assault on the mountain citadels. Things are far from static here, as a wide range of daily and annual temperatures causes minute contraction and expansion of rock particles. Stress and strain are produced by repeated volume changes. So although the Teton's rocks are extremely dense, they eventually yield and a crack forms. Water that seeps in along this surface of weakness freezes and expands, prying a slab of rock away from the mountain wall, either overnight or during long cold spells. Repeated frost wedging, as the process is known, eventually causes the slab to tip and fall. And what becomes of the rock slab? Well, depending on the slope of the mountain, it could fall and roll hundreds or thousands of feet. As it encounters obstacles, pieces break off. All of the fragments make their way to the valley floor or slope where they briefly rest. As a result, gravity moves rock debris over significant and easily observed distances. This debris is not stationary though. If it's mixed with snow or saturated with water, the entire mass may flow slowly like a glacier. Some can be seen on the south side of Granite Canyon, and one nearly a mile long can be found in the valley north of Eagle's Rest Peak. The numerous snow avalanches that thunder down mountainsides after heavy winter snowfalls also play a role in gravitational transport. Loose rocks and debris are carried down the mountainsides by the moving snow to the talus piles below. Trees, bushes, and soil are swept away from the slide sites, leaving visible scars down the slopes and exposing new rock surfaces to water and frost attacks. Many of the canyon trail's battered, broken, and uprooted trees bear silent witness to the awesome power of snowslides. And running water is another effective agent for transporting rock debris that has aided in the dissection of the Teton Range. The devastation caused by a broken water main on a roadbed is well known, as is the devastation caused by destructive floods. Spring floods in the Teton, swollen by melting snow and ice, annual precipitation, mostly snow, in the high parts average a layer of water 5 feet thick, move some rock debris onto the adjoining Jackson Hole floor. Now, the news of the crack at Teton understandably sends alarm bells ringing. Experts have discovered expanding cracks in the rock buttress, which geologists are closely monitoring for movement. Yellowstone is currently recharging as its magma chambers fill with molten rock from the Earth's mantle, the layer beneath the crust's surface. And scientists devised a new method last month to determine how quickly magma is building up beneath the Yellowstone supervolcano. The technique enables experts to precisely estimate the amount of magma entering the supervolcano from deep beneath the Earth's crust during the recharging process. While the new method cannot predict when Yellowstone will erupt, it may help scientists better understand how the volcano replenishes its deadly magma store. According to Washington State University researchers, these pools of molten volcanic rock form in subsurface magma chambers and are critical to the eruption process. The coal in the boiler is heating things up, study co-author Professor Peter Larson explained. It is like the boiler is heating up and the boiler is the source of the explosion. This allows us to know what is heating the boiler. Once these chambers are filled, the landform could erupt at any time, erupting months or millennia after a magma recharge. The eruption occurs when the magma chambers rupture, releasing up to 240 cubic miles or 1,000 cubic kilometers of magma into the atmosphere. An explosive, silica-rich volcanic rock called rhyolite that breaks through the Earth's crust during an eruption is a key driver of the volcano's destructive power. Professor Larson and his colleagues focused on the plume of magma heating the rhyolite from below in their new study. This gives us an idea of how much magma is recharging the volcano each year, Professor Larson explained. The researchers injected the stable radioactive isotope deuterium into several hot springs in Yellowstone National Park. According to the researchers, the chemical is safe for the environment and has been approved for use by park officials. The team's hot springs are linked to a network of hydrothermal vents that play an important role in the Yellowstone volcanic system. The amount of water and heat flowing out of the springs was calculated using the temperature of the springs and the time it took for the deuterium to return to normal background radiation levels. Previous studies, according to the researchers, underestimated the amount of water flowing through the springs and the amount of heat leaving the springs. This brings us to a question you might have been thinking about. Can a Yellowstone eruption be prevented, or are we helpless and destined to be sitting ducks if the volcano does decide to erupt? Well, NASA believes that drilling up to 6 miles or 10 kilometers into the supervolcano beneath Yellowstone National Park and pumping in high-pressure water could cool it. The mission will cost a whopping $3.46 billion. However, NASA considers it the most viable solution. However, on the positive side, using heat as a resource provides an opportunity to pay for the plan. It could be used to build a geothermal power plant which generates electricity at extremely competitive prices of around 10 cents per kilowatt hour. However, this method of subduing a supervolcano has a serious drawback, and that's the potential to backfire and cause the supervolcanic eruption that NASA is attempting to prevent. Drilling into the magma chamber's top would be very risky, but we could take our chances by carefully drilling from the lower sides. Aside from the potentially disastrous risks, the plan to cool Yellowstone through drilling is not simple. It would be an excruciatingly slow process that would occur at a rate of 1 meter per year, implying that it would take tens of thousands of years to completely cool it. And even then, there is no guarantee it will be successful for hundreds, if not thousands of years. So if NASA doesn't succeed in preventing a Yellowstone eruption, where does that leave us? If the supervolcano beneath Yellowstone National Park erupted again, it could spew ash thousands of miles across the country, damaging buildings, suffocating crops, and shutting down power plants. It would be a total disaster. And a 5-mile-deep reservoir of hot magma lurks beneath Yellowstone National Park, fed by a massive plume of molten rock welling up from hundreds of miles below. Many of the park's famous geysers and hot springs are the result of this heat, and as magma rises into the chamber and cools, the ground above rises and falls on a regular basis. That magma chamber has erupted a number of times in history. Now, the vast majority of Yellowstone's eruptions have been smaller lava flows, with the most recent occurring around 70,000 years ago at Pitchstone Plateau. But it's the remote possibility of catastrophic super-eruptions that draws so much attention to Yellowstone. A super-eruption is defined as anything with a magnitude of 8 or higher on the Volcano Explosivity Index that ejects at least 1,000 cubic kilometers or 240 cubic miles of material. That's enough to bury Texas 5 feet beneath the ground. These super-eruptions are thousands of times more powerful than even the most powerful eruptions we've seen in the past, including the 1980 Mount St. Helens eruption. Yellowstone has experienced 3 of these truly massive eruptions, 2.1 million years ago, 1.3 million years ago, and 664,000 years ago. The last of these, Yellowstone Lava Creek, ejected so much material from below that it created the Yellowstone Caldera, a 34-mile by 50-mile depression in the ground. It is worth noting that Yellowstone isn't the only supervolcano on the planet. Geologists have discovered evidence of at least 47 super-eruptions throughout Earth's history. The most recent occurred around 26,000 years ago in New Zealand's Lake Taupo. And more dramatically shifting tectonic plates caused the massive Toba eruption 74,000 years ago. This precipitated a dramatic 6 to 10-year global winter, which some believe nearly wiped out the nascent human race. Although this is not an absolute rule, the Earth has seen roughly one super-eruption every 100,000 years on average. One of the most likely Yellowstone eruption scenarios is a smaller event with lava flows, similar to what is currently happening at Iceland's Barabunga, and possibly a typical volcanic explosion. This would most likely be caused by a series of earthquakes in a specific area of the park as the magma rose to the surface. In the unlikely event of a much larger super-eruption, the warning signs would be much more pronounced. We'd most likely first notice intense seismic activity throughout the park, and before an eruption, those earthquakes could take weeks or months to break up the rocks above the magma. But what if there was a super-eruption, an event 1,000 times more powerful than a regular volcanic eruption that ejected at least 240 cubic miles of material and lasted weeks or months? The lava flows themselves would be contained within the park within a relatively small radius, say 40 miles or so. In fact, only about 1/3 of the material would ever reach the atmosphere. But most of the damage will come from volcanic ash, a mixture of splintered rock and glass that will be ejected miles into the air and dispersed across the country. Scientists used historical ash deposits as well as advanced modeling to conclude that an eruption would produce an umbrella cloud that would spread in all directions. A supereruption could bury the northern Rockies in 3 feet of ash, wreaking havoc on Wyoming, Idaho, Colorado, Montana, and Utah. Meanwhile, the Midwest would receive a few inches of ash, while both coasts would receive even less. The precise distribution would be determined by the season and weather patterns. However, any of those scenarios would be disastrous. That much volcanic ash has the potential to kill people, plants, and animals, as well as crush buildings. Even a few inches of ash, which much of the country may receive, can destroy farms, clog roadways, cause serious respiratory problems, block sewer lines, and even short out transformers. Much of North America's air travel would be forced to a halt. Such a large volcanic eruption would also have a significant impact on the global climate. Volcanoes can spew sulfur aerosols into the atmosphere, which reflect sunlight and cool the climate. Because these particles have a short lifetime in the atmosphere, their effect is only temporary, but it can be dramatic. When Mount Pinatubo erupted in 1991, it cooled the planet by approximately 1 degree Celsius or 1.8 degrees Fahrenheit for several years. And the Tambora eruption in 1815 cooled the planet sufficiently enough to damage crops all over the world, potentially resulting in famines that were seen in some areas. And those were minor eruptions in comparison to what a supervolcano is capable of. There could, however, be some good news. Yellowstone has already lived a long and fruitful life. It's possible that the last eruption was the last. After all, volcanoes do die out. The magma chamber beneath Yellowstone is being influenced by 2 opposing forces: heat from below and relative cold from the surface. If less heat enters from below, the chamber could potentially freeze, eventually transforming into a solid granite body. It is also worth noting that the volcanic hotspot beneath Yellowstone is gradually moving northeast, or more accurately, the North American tectonic plate above the hotspot is migrating southwest. On a long enough timescale, the hotspot will move out from beneath Yellowstone, and the supervolcano will presumably die out. How do you think a Yellowstone eruption will affect you? Let's hear you in the comment section below.